Chapter 1. Birth of a Giant. May 1995. The Norwegian coastline. Thousands of people stand along the shore, families with children, some having traveled hundreds of kilometers. They are staring out to sea. There, gliding slowly across the water, moves something so enormous that at first it seems like an optical illusion. A concrete structure 472 meters tall, taller than the Eiffel Tower, crawls past the Norwegian fjords at the pace of a walking man. 11 tugboats pull it with steel cables as thick as a human arm. On national television, commentators speak in hushed voices, as though afraid to break the spell. This is the Troll A platform, and it is heading somewhere no man-made object has ever gone before. To the bottom of the North Sea, under 303 meters of water, to stand there for the next half-century. But to understand why this moment entered the history of engineering forever, you need to start not with the tow. You need to start with how something like this is born at all, and why this entire colossus begins its life not in the sea, but on land, in an enormous pit filled with concrete. By the late 1960s, the North Sea had become Europe's primary oil arena. Geologists had long suspected that colossal reserves of hydrocarbons lay beneath its floor, but reaching them was technically impossible. Depths here reach several hundred meters, storms persist for months, and water temperatures in winter drop to near zero. The first platforms attempted in this region were relatively small and fixed to the seabed with piles, like giant metal tables driven into the ocean floor. This approach worked at shallow depths, but as oil companies pushed further from shore, depths increased and steel pile foundations became less practical. Too expensive, too complex, too vulnerable to waves and currents. Engineers needed a fundamentally different solution, and they found one, borrowing a principle more than 2,000 years old. Archimedes formulated his law in the 3rd century BC. A body submerged in a liquid displaces a volume of liquid equal to its own volume and receives a buoyant force equal to the weight of that liquid. This is why a steel ship floats, not because steel is lighter than water, but because there is enough air inside the hull that the average density of the entire structure is less than the density of water. Norwegian engineers applied that same logic to an object with no precedent in the history of construction. They designed the platform's foundation as enormous hollow concrete columns, not solid, not monolithic, but hollow, with air sealed inside. That trapped air turned the columns into floats, and a structure weighing hundreds of thousands of tons could sit on the surface of the water as confidently as an ordinary boat. But before reaching the water, the platform is built on land. In a massive dry dock, a pit from which water has been temporarily excluded, workers shape the lower section of the structure. The material used here is not ordinary concrete. Norwegian structural engineer Terje Lusset, in his monograph on the design of offshore gravity platforms, described this material as a compound that behaves more like metal under load, capable of minor deformation that distributes pressure across the structure without cracking or crumbling. The walls are reinforced with a dense mesh of steel rods. The columns are engineered with a safety margin calculated for the water pressure at depths of 300 meters and beyond, pressure that would simply pulverize standard concrete within a few years. When the foundation is complete, water is admitted to the dry dock. Slowly, under control, and the colossal concrete structure, heavier than most military aircraft carriers, begins to rise. Against all intuition, it floats. The secret is simple and brilliant at once. Air sealed inside the hollow concrete tanks acts as a buoy. On the floating foundation, the upper deck is assembled. Living quarters, drilling derricks, processing systems, helicopter pads. The platform takes its final shape on the water, close to shore, while cranes, materials, and workers are still within reach. Only when everything is ready does what Norwegians watched from the shore in May 1995 begin. Moving a platform with a total weight exceeding 1 million tons is an operation with no margin for error. The tugboats form a wedge and pull the structure at about 5 kilometers per hour. Faster is not possible. At higher speeds, waves create lateral forces capable of deforming the hull before it even arrives. The most critical moments come when the Colossus passes through narrow coastal channels, rocks on either side, unpredictable currents, gusts of wind. If one of the cables snaps under load, the recoil energy instantly disables the tug's equipment, and the entire operation is in jeopardy. Captains work at the limit of their concentration for 7 straight days. The journey from the shipyard to the drilling site covers 200 kilometers and takes 7 days. At the destination, engineers open the valves. Seawater rushes into the hollow columns of the foundation, the very same ones that had kept the platform afloat. Air is expelled, and the giant structure begins to sink slowly. The descent is strictly controlled. Operators regulate the rate of flooding in each column independently so the platform lowers evenly without tilting. When the concrete foundation reaches the bottom, its steel skirts are literally pressed into the seabed under the weight of hundreds of thousands of tons. The space beneath them is then filled with cement, and the artificial island fuses permanently with the ocean floor. No piles, no additional anchors. Only its own weight, holding the structure in place as reliably as gravity holds mountains. This is why such platforms are called gravity-based structures. Troll A settled on the floor of the North Sea on May 17, 1995, Norwegian Constitution Day, a coincidence that Norwegians took as a symbol. A platform built over 9 years, towed for 7 days, lowered to the seabed over several hours, now standing where it would stand for the next 50 years. Motionless, positioned with an accuracy of a few meters for an object nearly half a kilometer tall. From the outside, it looked like a triumph. Engineers had done what seemed impossible, built and installed the tallest structure ever moved across the surface of the earth. But inside the platform at that moment, there was nothing but empty corridors, cold metal and darkness. For this industrial colossus to come alive, for light, heat, food, air, and hundreds of living people to appear inside it, people who would spend months here at a stretch, an entirely different kind of problem remained to be solved. How do you sustain full human life in complete isolation, dozens of kilometers from shore, when the only connection to the world is a helicopter that a storm might ground for days? Chapter 2. A City in the Middle of the Ocean, Chapter 2. A City in the Middle of the Ocean. Imagine waking up in the morning and looking out the porthole to see nothing but water stretching to the horizon. No streets, no shops, no hospitals. The nearest city is 100 kilometers away in a straight line, but you can only get there by helicopter, if the weather allows. You cannot simply step outside for fresh air. Outside, the wind is force 7, and the temperature is -20. You cannot call an ambulance. There is no ambulance here, and you cannot quit mid-shift and go home. Your contract forbids it, and the helicopter will not come for another 2 weeks. Welcome to an offshore oil platform, a place where several hundred people live and work in conditions that nature never designed humans for, and a place that must operate without interruption, because every minute of downtime translates into hundreds of thousands of dollars in losses. To understand how this is even possible, you need to grasp one fundamental thing. An offshore platform is not simply an industrial facility. In its internal logic, it is far closer to a space station or a nuclear submarine than to an ordinary factory. Everything that urban infrastructure provides on land, electricity, water, sewage, medicine, food, air, must here be produced or delivered independently, in conditions of constant motion, salt fog, and storm force wind. Soviet researcher Vladimir Kuznetsov, in his 1987 work on life support systems for offshore drilling platforms, wrote that designing the life support systems of a platform is more complex than designing the structure itself, because the structure only needs to stand, while the life support systems must function without failure under any conditions, including those that no one can predict in advance. The heart of the entire platform is its power system. Without electricity, nothing here works. Not the drilling equipment, not the heating systems, not the pumps, not the lighting, not communications. A power outage lasting even a few minutes in the middle of an Arctic storm is not a malfunction. It is a catastrophe. This is why the primary energy source on most modern platforms is gas turbines running on associated gas, the very gas produced alongside the oil. The platform literally feeds on its own output. This solution is simultaneously economical and logical. Gas that would otherwise have to be flared off or re-injected into the reservoir goes directly into the turbines and becomes electricity. On the Russian platform Berkut, operating in the Sea of Okhotsk, the installed generator capacity is around 72 megawatts, enough to power a small Russian city. And yet this platform sits in one of the most hostile seas on the planet, where winter temperatures drop to minus 45 degrees Celsius and pack ice exerts pressure capable of crushing the steel hull of a ship. But gas turbines are only the first layer of protection. In the event of their failure, every platform has a backup diesel generator capable of taking over the critical systems. And in the event that the backup generator fails, battery banks that give personnel enough time either to restart the backup or begin evacuation. Norwegian engineer Erik Hagen, in his study of power supply reliability on offshore platforms published in Offshore Technology Journal in 2003, described this system as a matryoshka of safety. Each successive layer of protection activates only when the one before it stops coping. Water is the next most critical problem. On most Caribbean and Pacific platforms, fresh water simply does not exist in the surrounding environment. The ocean is 97% of all the water on Earth, and all of it is salt water, unsuitable for drinking or for technical use. The solution is desalination plants running around the clock, converting seawater into drinking water through reverse osmosis. The plant's membranes retain salt and impurities while allowing only water molecules to pass through. On a large platform, such a system produces between 100 and 300 cubic meters of fresh water per day, enough for the entire crew several times over. At the same time, air filtration systems run continuously. The enclosed spaces of the platform require constant air exchange, removal of industrial vapors, and humidity control. On Arctic platforms, air is preheated before entering the living quarters. Otherwise, the heating system simply cannot compensate for the volume of heat lost through ventilation. Supply logistics is a separate operation that never pauses for a single day. Fresh food, medicines, spare parts, rotating personnel. All of it must be delivered regularly across tens or hundreds of kilometers of open water. Helicopters fly on schedule, but their schedule depends entirely on the weather. Below a certain visibility minimum, or above a certain wind threshold, the helicopter simply does not fly. Heavy cargo is carried by supply vessels, purpose-built ships with dynamic positioning systems that allow them to hold station beside the platform in rough seas. Deck cranes lift containers weighing several tons directly from a pitching ship's deck. An operation that would take minutes in a port can stretch to several hours here, depending on wave height and wind gusts. Among newcomers arriving on a platform for the first time, anxiety about supply interruptions is common. What if a prolonged storm cuts off deliveries? In practice, every platform maintains a strategic reserve of food, medicines, and critical spare parts calculated to sustain fully autonomous operation for a minimum of several weeks. This is not optional. It is a requirement of international safety standards, codified in International Maritime Organization documents since the 1970s and consistently tightened after every major industry accident. Inside the platform, a rhythm of life unlike anything on land takes hold. Personnel work on a rotation system, typically 12 hours of work alternate with 12 hours of rest, with no days off throughout the entire shift. A shift lasts from 2 to 4 weeks, after which the worker flies home for an equivalent period. The working day here begins and ends not by the sun, but by the clock. In the Arctic winter, the sun may not appear for weeks, while in the tropics it shines identically year-round. Psychologists who study human behavior in isolated industrial environments, among them Nicholas Corcoran of the University of Aberdeen, in his work on the psychological health of offshore platform workers, note that disruption of the natural light cycle is one of the primary sources of stress for personnel, particularly during early rotations. To compensate for the rigid schedule and total isolation, operators of major platforms invest significantly in the quality of daily life. Canteens operate around the clock and offer 4 meals a day. Cooks on a platform are considered among the most important members of the crew, because food remains one of the few reliable sources of pleasure in an enclosed environment. There are gyms, saunas, recreation rooms with television and internet access. Some Norwegian platforms even have small cinemas. This investment in personnel welfare is not charity. Oil companies worked out long ago that staff turnover and reduced productivity caused by poor living conditions cost more than the investment in comfort. The Berkut platform in the Sea of Okhotsk is one of the most instructive examples of how far the concept of an autonomous industrial island can be taken. In winter, when the sea freezes and marine supply operations cease entirely, the platform switches to helicopter bridge mode. All living modules are protected by multi-layer thermal insulation. Deck heating systems prevent ice forming on working surfaces. Pipelines and equipment are enclosed in heated casings. At -45 outside, comfortable temperatures are maintained inside the living quarters, and drilling operations continue in normal mode. All of this, an extraordinarily complex infrastructure that functions every minute of every day while the platform stands at sea, makes it possible for hundreds of people to live, eat, sleep, and do their work in the middle of the ocean. But the platform itself is only a home and a workplace. The actual purpose for which all of this was built, for which the helicopters fly and the supply ships sail, lies not on the surface of the water. It lies several kilometers deeper, beneath the ocean floor, in rock formations millions of years old. And to reach it, engineers had to develop a technology that can, without exaggeration, be called surgery on the Earth's crust, an operation conducted blind, at a distance of several kilometers, in total darkness, under crushing pressure. Chapter 3. Piercing the Earth's crust. 1 kilometer of water beneath the keel, then another kilometer of rock, then 2 more. Somewhere down there, in absolute darkness, under pressure that would crush a human being in a fraction of a second, lies an oil-bearing formation. It cannot be seen. It cannot be touched. You cannot check whether you are moving in the right direction simply by looking out a window. And yet engineers must drill a precise channel to reach it, less than a meter in diameter, several kilometers long, through layers of granite, limestone, and shale that took hundreds of millions of years to form. The required accuracy is a matter of meters, at a depth of several kilometers, in complete darkness. To understand why this is even possible, you need to start with the nature of the task itself. Oil and gas do not pool in underground lakes, as popular imagination tends to picture. They saturate porous rock formations, sandstones, limestones, the way water saturates a sponge. These formations may lie anywhere from 1 to several kilometers below the seabed, and the seabed itself may already be several hundred meters beneath the water's surface. Geologists locate the formations using seismic surveying. Ships send sound waves down through the water. The waves reflect off different rock layers and return to the surface, and computers construct a three-dimensional map of what lies beneath the floor. This map gives an approximate picture of where to look. Only drilling will reveal whether oil is actually there. Drilling begins with a drill string being lowered from the platform to the seabed, a composite pipe assembled from individual sections screwed together one by one as the well deepens. At the bottom of the string is a drill bit, fitted with tungsten carbide teeth or diamond inserts. The bit rotates and breaks apart the rock. In principle, this is nothing radically new. Humans have been drilling into the earth for thousands of years, but the scale and conditions here turn every element of the process into a distinct engineering problem. The first problem is heat. At depths of several kilometers, rock temperatures can reach 200 degrees Celsius and beyond. A drill bit rotating in such an environment heats from friction to temperatures at which ordinary steel loses its strength within minutes. The solution that the oil industry has applied since the mid-20th century is drilling fluid, continuously pumped down through the drill string, washing over the bit, cooling it, and rising back up through the annular space between the string and the borehole wall, carrying ground rock cuttings with it. This fluid is not simply water. It is a carefully engineered mixture, formulated individually for each well. It must be dense enough to hold back the formation pressure and prevent oil or gas from escaping before the well is ready, yet fluid enough to circulate along the entire length of the string. British drilling fluid specialist John Worley, in his monograph Drilling Fluids Technology, a standard textbook for petroleum engineers, compared drilling fluid to the blood of the well. Remove it, and the entire system fails immediately. The second problem is pressure. At great depths, rock formations are under colossal pressure from the overlying layers. When the bit penetrates an oil-bearing formation, that pressure begins pushing the formation's contents up through the wellbore. If left uncontrolled, oil and gas will surge to the surface with explosive force. This is precisely what happened on the Deepwater Horizon platform in the Gulf of Mexico in April 2010. An uncontrolled gas blowout, ignition, explosion, the deaths of 11 people, and the largest oil spill in United States history. The investigation conducted by the National Commission on the BP Deepwater Horizon oil spill established that the critical failure was in the system designed specifically to prevent that outcome, the blowout preventer. The blowout preventer is a device weighing several hundred tons, installed directly on the seabed above the wellhead. In function, it resembles an emergency valve, except that instead of simply blocking flow, it is equipped with powerful hydraulic blades capable of shearing through the entire drill string and sealing the well hermetically. The command to activate can come from an operator on the platform or automatically from pressure sensors. Under normal conditions, the blowout preventer is never used. It simply sits on the seabed and waits. But its presence is a mandatory condition for obtaining a drilling permit in any jurisdiction in the world. The third problem is navigation. Wells are rarely drilled straight down. The oil-bearing formation may not lie directly beneath the platform, but off to one side. Beyond that, it is economically efficient to drill multiple wells from a single surface point in different directions, reaching the maximum possible area of the reservoir. This gave rise to directional drilling, a technology that allows the well to be deflected from vertical by tens of degrees and steered along a planned trajectory toward a specific target in the formation. On the Berkut platform in the Sea of Okhotsk, wells were drilled with horizontal departures of more than 12 kilometers from the drilling point, a world record at the time of their completion. To put that in perspective, the drill string descended vertically and then curved gradually, traveling horizontally a distance comparable to the length of several large city districts, with a positional accuracy of a few meters. How is it possible to steer a drill bit several kilometers underground from the surface? The answer is real-time telemetry. Near the bottom of the drill string, adjacent to the bit, sits a block of measuring instruments: inclinometers, gyroscopes, pressure, and temperature sensors. These instruments continuously record the position of the bit in space and transmit data to the surface through pressure pulses in the drilling fluid, a kind of Morse code where changes in pressure encode numerical information. Operators on the platform see on their screens exactly where the bit is located, in which direction it is moving, and how far it deviates from the planned trajectory. When correction is needed, a specialized deflection tool, a downhole motor, adjusts the drilling angle. Once a well has been drilled to its target depth, the borehole walls are reinforced. A steel casing pipe is run in, and cement slurry is pumped into the space between the pipe and the rock. The cement sets, creating a reliable barrier between formations and preventing cross-flow between layers. Only then are perforations made through the lower section of the casing at the level of the oil-bearing formation, and oil begins entering the well under the pressure of the reservoir itself. The entire process, from the start of drilling to first oil, takes anywhere from several weeks to several months per well on an offshore platform. A major field may have several dozen such wells. Each one is a separate operation with its own geological characteristics, its own pressure regime, its own temperature profile, and its own risks. And while the drilling crew works on a new well, the wells already in production pump oil continuously, day and night, in storms and in calm. But what rises from the wells to the platform deck cannot simply be pumped into a tanker and sent ashore. What comes up from below is not oil in any familiar sense of the word. It is a complex mixture that must first be separated into its components right here, on the deck, hundreds of kilometers from the nearest refinery. And this is where the part of the platform's work that almost no one knows about begins, because from the outside it is invisible, and from the inside it looks not like oil production, but like a chemical plant in the middle of the ocean. Chapter 4. The enemy outside 30 meters. That is the height of the wave that crashed into the Chinese deepwater platform Haishi during one of the Pacific typhoons. 30 meters, a 10-story residential building falling on you from above at the speed of an express train. The multi-ton wall of water struck the steel hull with such force that seismic sensors on the shore registered the impact. The platform listed. The lights in the living quarters went out. The crew sat in darkness, listening to the wind howling outside and the metal groaning under loads it seemed never to have been designed for. The automated systems at that moment were fighting for the survival of the structure without any human involvement. And the platform held. But to understand why it held, rather than why it should have collapsed, you need to understand what an offshore platform actually contends with every single day of its working life. The ocean is not simply the backdrop for oil production. It is an active, hostile environment that bears down on the structure from every direction simultaneously and never stops. Waves, currents, wind, temperature swings, salt corrosion, marine organisms colonizing underwater surfaces. All of it works against the platform around the clock, year after year. Engineers who design offshore structures work with the concept of metal fatigue, the gradual degradation of a material under cyclic loading, where individual loads cause no visible damage, but their cumulative effect over years creates micro cracks that eventually grow into fractures. Norwegian researcher Torbjørn Moe, in his doctoral dissertation on fatigue life prediction for offshore steel structures, submitted to the Norwegian University of Science and Technology, demonstrated that in North Sea conditions, the steel joints of a platform undergo between several million and several tens of millions of load cycles per year from wave action alone. Every wave is one cycle. The waves never stop. This is precisely why the shape of a modern offshore platform is not accidental. Every curve of the hull, every angle of the column supports, every transition radius between structural elements, all of it is the product of thousands of hours of hydrodynamic calculations and testing in wave tanks. The goal is not to resist waves through brute frontal strength, but to distribute their energy across the entire structure so that no single point absorbs a critical load. Living modules are deliberately elevated as high as possible above the waterline, so that even an abnormally large wave does not reach inhabited spaces. Lower decks, where equipment is located, are designed with the expectation of periodic flooding and drying. But waves are a predictable adversary. Far more dangerous are what oceanographers call rogue waves or freak waves. Until the late 20th century, their existence was considered maritime folklore. Legends of walls of water 20 or 30 meters high, supposedly rising from nowhere in relatively calm seas. The scientific community treated these accounts with skepticism, until in January 1995, the sensors on the Draupner platform in the North Sea recorded a wave 25.6 meters high against an average sea state of around 12 meters. It was the first instrumentally confirmed rogue wave in history. Professor Alfredo Osborne of the University of Turin, one of the leading researchers of this phenomenon, explained in his book Nonlinear Ocean Waves that such waves arise from the nonlinear interaction of multiple wave systems in which the energy of many waves focuses at a single point in space and time. Predicting such an event with any reasonable precision remains beyond the current capability of science. For platform designers, the discovery of rogue waves meant reconsidering all calculated load assumptions. Where engineers had previously relied on statistical models of maximum wave heights based on historical observations, it became clear that real extreme loads could substantially exceed these estimates. Modern platforms are designed with safety margins that account for the possibility of encountering a rogue wave, though the precise parameters of such waves remain a subject of ongoing scientific debate. In high latitudes, ice compounds the threat. For platforms operating in Arctic and subarctic seas, ice loading is one of the primary design parameters. Pack ice driven by wind and currents generates pressure that at peak values can reach several megapascals per square meter of surface area. Pressure capable of crushing the steel hull of a ship not designed for ice operations. For a fixed platform that cannot move out of the path of an ice field, this means building a structure that can withstand a direct strike from a moving body of ice. The Berkut platform in the Sea of Okhotsk is designed to withstand the impact of an ice mass of up to 2 million cubic meters, roughly equivalent to a small iceberg. The platform's foundation in the ice impact zone has a conical shape. Rather than receiving the ice load horizontally, the cone deflects it upward, breaking the ice field by bending rather than by compression. This principle has been used in icebreaker design since the 19th century, but applying it to a stationary structure the size of a multi-story building required separate engineering solutions. In the North Atlantic and in the seas around Canada, icebergs are the threat. They move slowly, but their mass is such that the kinetic energy of even a modest iceberg is comparable to the energy of an explosion. For platforms operating in zones of heavy iceberg traffic, particularly off the coast of Newfoundland, where the Hibernia and Terra Nova oil fields are located, a dedicated iceberg monitoring and management system has been developed. aircraft and vessels maintain continuous surveillance of ice movements. When an iceberg moves on a course threatening the platform, specialized vessels attempt to tow it aside using cables. If towing fails, the platform issues an alert and personnel move to a heightened state of readiness. In extreme cases, semi-submersible platforms equipped with their own thrusters can slowly move clear, but this is a last resort, rarely used. All of this, waves, ice, icebergs, storm force winds, represents threats that are visible and at least partially foreseeable. Sensors detect them. Radars track them. Meteorologists provide advance warning. The crew has time to prepare. But inside the platform itself, flowing through pipelines and tanks, through pumps and separators, are substances that at the slightest error turn an industrial facility into an inferno within seconds. Against this adversary, neither hull shape nor ice protection nor dynamic positioning is of any use. Against fire on a platform, an entirely different kind of battle is fought, and its rules are completely different. Chapter 5. The Enemy Within. In August 1988, the Piper Alpha platform in the North Sea burned for 120 minutes. In that time, 167 people died out of the 226 on board. It remains the deadliest disaster in the history of offshore oil production, and it transformed the entire industry so fundamentally that engineers divide the history of offshore safety into two eras, before Piper Alpha and after. The cause was not a natural catastrophe, not the failure of complex equipment, and not an improbable chain of coincidences. The cause was a leak of gas condensate from a pump returned to service without proper verification after maintenance. A small cloud of gas, a source of ignition, an explosion, and then an uncontrolled chain reaction that no firefighting system could stop because none had been designed for that scenario. Piper Alpha did not become simply a tragedy. It became a textbook. The inquiry conducted by Lord William Cullen and published in 1990 as a 2-volume report, still referred to simply as the Cullen Report, contained 106 recommendations for the revision of safety standards. The majority were adopted as mandatory requirements in all oil-producing countries. It was after Piper Alpha that platforms acquired fire division systems separating the facility into independent zones, fundamentally redesigned maintenance protocols, and evacuation system requirements that remain in force to this day. A fire on an offshore oil platform is not the same as a fire on land. On land, a burning building can be evacuated. Firefighters arrive within minutes. A burning building can be walked around. On a platform, there is nowhere to go. Water surrounds it on all sides. Firefighters will not arrive. The nearest fire station is 100 kilometers away. And a burning module cannot be walked around if the route to the lifeboat stations runs through it. This is precisely why fire protection systems on a platform are designed not as means of extinguishment, but as means of containment, buying time for evacuation. The first layer of protection is detection. The entire platform is covered by a network of sensors responding to smoke, heat, the presence of combustible gases, and changes in oxygen concentration. The sensors operate across different sensitivity ranges and back each other up. If one type of sensor gives a false reading, another type will confirm or refute it. Modern fire detection systems on platforms, according to data from the Norwegian Petroleum Directorate, can detect a combustible gas leak at concentrations several times below the lower explosive limit, long before the mixture becomes capable of igniting. The second layer is isolation. The entire platform is divided into fire zones, separated by bulkheads made from specialist fire-resistant materials. These bulkheads can withstand fire for several hours, preventing flames from spreading from one section to another. The moment the detection system identifies signs of fire, fire doors and ventilation dampers close automatically, cutting off the oxygen supply and preventing the spread of smoke. The alarm system activates simultaneously, and crew begin moving along evacuation routes. The third layer is suppression. Around the platform's process equipment, separators, compressors, pipelines, fixed firefighting systems are positioned. Some use water in the form of fine mist, which strips heat from burning surfaces and displaces oxygen. Others use foam, particularly where oil or other liquid hydrocarbons are burning, since ordinary water does not extinguish them, but instead scatters the burning liquid, expanding the fire zone. In particularly critical areas, where sensitive equipment or control systems are located, gas suppression systems using inert gases or specialist chemical agents are used, agents that extinguish fire without damaging electronics. Robotic water cannons mounted on rotating platforms can direct water streams to any point on the open deck automatically, without human intervention. Alongside suppression runs cooling. One of the primary risks in a platform fire is not the flames themselves, but the heating of adjacent pipelines and tanks to temperatures at which they lose structural integrity or internal pressure rises to critical levels. This is precisely how the second, far more powerful explosion occurred on Piper Alpha, when the heat of the initial blast ruptured the tartan gas pipeline supplying gas from a neighboring platform. Water spray systems covering the steel structures near the seat of a fire prevent the metal from overheating, even when the fire cannot be immediately extinguished. Evacuation is the final and most critical element. Every platform provides several means of leaving the vessel. Lifeboats that can be launched in heavy seas, life rafts, helicopter landing pads, and on some platforms, dedicated escape chutes directly to the water with survival suits. After Piper Alpha, evacuation system requirements were radically tightened. Every platform worker must undergo regular evacuation drills, all routes must be clearly marked and unobstructed, and the time for full evacuation is standardized and regularly audited. One of the hardest lessons the industry absorbed from Piper Alpha concerns not equipment, but human behavior. That night, many of those who could have survived did not, because they waited for an official evacuation order that never came, as the control center had been destroyed. People remained in their quarters, following the instruction to await directions, while fire cut off escape routes. American organizational safety scholar Carl Weick, in his article on the collapse of sense-making in organizations published in Administrative Science Quarterly, analyzed situations of this kind and showed that in sudden catastrophes, rigid hierarchical procedures frequently become a fatal trap. After Piper Alpha, safety standards were amended to give any platform worker the right to independently decide to evacuate without waiting for an official order. Today, fire safety on offshore platforms is not simply a collection of technical systems. It is a design philosophy running through every decision, from the choice of bulkhead lining materials to the routing of pipelines, from the placement of emergency exits to the logic of automated systems. A platform is built so that when fire breaks out, every person on board has enough time to reach a means of survival. Not to defeat the fire, that is often impossible, but to give people time to get out. And yet, however sophisticated the protection against external storms and internal fires may be, there is a threat that none of these systems can address. A threat that comes neither from outside nor from the surface, but from the depths below, traveling up through steel pipes as anomalies of pressure that engineers cannot always explain immediately. And in those moments, when instruments begin showing what should not be there by any calculation, the platform finds itself on the most dangerous frontier of all. Chapter 6. The Voice from the Deep. 3 a.m. A platform in the Gulf of Mexico operating in normal mode. The watch operator in the control room looks at screens displaying pressure, temperature, and flow readings. Everything is nominal. Then one sensor spikes, then another. then a third, already into the red zone. The automation responds in fractions of a second, faster than the operator can process what is happening. Powerful pumps stop, the rotation of the drill bit ceases, a siren splits the night quiet of the platform. Something is rising from the depths, along a steel column several kilometers long, that should not be there. Exactly what? No one on the surface yet knows. Events like this on drilling platforms are called kicks, a sudden upward pressure impulse from below. They occur when the pressure in the drilling fluid filling the wellbore proves insufficient to hold back the formation pressure. Oil, gas, or water from the formation begins entering the well and rising towards the surface. If the situation is not brought under control immediately, the kick becomes an uncontrolled blowout, and that is precisely the initiating event of the Deepwater Horizon catastrophe. But a kick is an event with a physical explanation and an established response protocol. Far more complex are anomalies that sensors register as deviations from normal, but that do not fit standard scenarios. At great depths, where the drilling tool passes through geological layers hundreds of millions of years old, zones of abnormally high formation pressure are encountered, so-called trapped pressure zones, in which pressure has been preserved since the formation of the rock, and may far exceed that of the surrounding layers. When the bit penetrates such a zone, pressure changes sharply, and that change travels up the drill string at the speed of sound in metal, approximately 5,000 meters per second. Surface sensors register it almost instantaneously, but interpreting it correctly is not always straightforward. Wellbore acoustics is a separate and poorly understood field. Along a steel pipe several kilometers long, filled with drilling fluid, sound waves propagate, reflecting off inhomogeneities in the well, interfering with each other and producing at the surface a complex pattern of acoustic signals. Experienced drilling engineers can read this pattern, a low rhythmic hum, building vibration, a shift in the tone of pump noise, the way a doctor reads an electrocardiogram. American geophysicist Martin Turner, in his work on acoustic monitoring of drilling operations published in the journal SPE Drilling and Completion, described these signals as the language of the well, a set of acoustic patterns, each carrying information about what is happening at depth. No algorithm has yet fully mastered this language. Only an experienced human being, with years spent on a rig, comes close. This is why, despite all the automation of modern platforms, the human being remains the critical element in emergency situations. Automation stops equipment in milliseconds, faster than any human can press a button. But the decision about what happened and what to do next is made by the driller, drawing on experience, intuition, and intimate knowledge of the specific well. After an emergency shutdown, the crew methodically works through instrument readings, analyses the pattern of pressure changes, assesses the volume and composition of fluid that entered the wellbore. Every action is logged. Every decision is coordinated with the onshore support center, where geologists and drilling engineers are on duty around the clock. This is not panic. It is precise, methodical work under conditions of uncertainty. In 2013, during drilling on one of the deepwater platforms in the Norwegian Sea, exactly such an incident occurred. Sensors registered anomalous pressure behavior at a depth of around 4,000 meters. Automation locked the well. Analysis revealed that the bit had entered a zone of abnormally low formation pressure, a depleted zone, where pressure was far below expected values. Drilling fluid began being absorbed by the rock instead of circulating through the well. The situation was the opposite of a kick, but no less dangerous. Loss of circulation meant loss of pressure control in the wellbore. The crew spent several hours restoring circulation by pumping a specialized plugging compound into the well. The operation was successful. In the logbook, the event occupied several pages of technical description. In the news, it did not appear. Most anomalies that sensors on deep-water platforms register are resolved exactly this way, without catastrophe, without casualties, without headlines. This is the result not of luck, but of decades of work on detection systems, response protocols, and personnel training. After every serious incident, whether Piper Alpha, Deepwater Horizon, or less well-known accidents that claimed fewer lives, the industry revised its standards, tightened requirements, and developed new technical solutions. This process is not complete. It will never be complete, because each new well goes deeper, each new field presents more complex geological conditions, and every time, humanity finds itself on the boundary between what it already knows how to do and what it has yet to learn. Today, more than 700 offshore oil platforms are operating in the world's oceans. They stand in the North Sea and the Gulf of Mexico, in the Sea of Okhotsk, and off the coast of Brazil, in West African waters, and in the South China Sea. Each of them is a compromise between what humans want and what nature permits. A compromise that demands from engineers, geologists, drillers, and operators the utmost precision, the utmost caution, and the utmost professionalism every single day. Because the ocean does not forgive mistakes. It never has. Beneath each of these platforms, in darkness and silence, several kilometers below, the wells continue their work. Drilling fluid circulates. Pressure is monitored. Oil rises to the surface. And somewhere down there, in the deepest and most ancient layers of the Earth's crust, layers that humanity is only beginning to reach, lie answers to questions that geologists have not yet learned to ask correctly.